Good day everyone. In this video, I will talk about mathematical problems involving patterns. Before I start, I prepared an icebreaker for you to have fun while watching. Number 1. Find the missing term. The answer is C, 20. Number 2. There are 4 floors in the hotel. The higher the floor, the more people live there. Which floor does the elevator go most often? The answer is A, 1. Number 3. There are 10 fingers on 2 hands. How many fingers are there on 10 hands? The answer is B, 50. The study of mathematics includes numbers and the different patterns. There are different types of patterns in mathematics, such as number patterns, image patterns, logic patterns, word patterns, and so on. The number pattern is the most commonly used since students are aware of even numbers, odd numbers, skip counting, and so on, which help in understanding these patterns easily. In mathematics, patterns include a series or sequence that generally repeat itself. The patterns that we observe in our daily lives are those of colors, actions, shapes, numbers, and so on. They can be related to any event or object and can be finite or infinite. In mathematics, patterns are a set of numbers arranged in a sequence such that they are related to each other in a specific rule. These rules define a way to calculate or solve problems. Here's a few examples of mathematical problems involving patterns. Let's try to answer example 1. Here is a list of months and a code for each. The question is, what is the code for the month of September? The answer is 9119. What is the pattern? At first, we may not readily see any pattern. This would make us think we cannot solve this problem. However, we should not give up. We just have to read the problem and try to find any existing pattern. By careful observation, it appears that the codes for January, June, and July contain 10 as their last 2 digits. This observation is also true for March and May, which contain 13 in their codes. Hence, this gives us the idea that there must be common to these months, such that these are also common in their codes. January, June, and July all starts with letter J. March and May starts with letter M. The letter J is the 10th letter of the English alphabet, while letter M is the 13th letter. Observing this pattern, it becomes obvious that the last digit or last 2 digits in each code will correspond to the position of the first letter of each month in the English alphabet. By logical reasoning, it becomes clear that the last digit for the code of February is 6, since letter F is the 6th letter of the English alphabet. This is also true for April and August, with the last digit in its code as 1. With this, we can now say that the last digit in the code for September will be 19, considering the S is the 19th letter of the English alphabet. There are patterns in the first and second digits of each month's code. There are a total of 7 letters in the month of January. The first digit is therefore 7. The first month of the year is January, so 1 is the second digit. Now that we know that September has a total of 9 letters, we can say that the first digit in the code for September is 9. September is the 9th month on the calendar, so the second digit in the code is 9. We get the code for September as 9919 by looking at these numerical patterns. For the example 2, find the missing number to replace the question mark. The pattern in the picture is that the numbers in the circles are the sum of the two digits in the opposite quadrants of main circle. In this case, the number in place of the question mark is 5 plus 7 equals 12, so the answer is 12. In example 3, what is next in sequence 2, 5, 8, 11, 14? To answer this question, we often construct difference table, which shows the differences between successive terms of the sequence, so we are going to use this method. Each of the numbers in row of the table is the difference between the two closest numbers just above it. The differences in row are called the first differences of the sequence. In this case, the first differences are all the same. Thus, if we use the above difference table to predict the next number in the sequence, we predict that 14 plus 3 equals 17 is the next term of the sequence. This prediction might be wrong, however, the pattern shown by the first differences seems to indicate that each successive term is 3 larger than the preceding term. In example 4, what is next in sequence 5, 12, 27, 44, 65? In this table, the first differences are not all the same. In such a situation, it is often helpful to compute the successive differences of the first differences. These are shown in second differences. To predict the next term of a sequence, we often look for a pattern in a row of differences. For instance, in the following table, the second differences shown in blue are all the same constant, namely 4. If the pattern continues, then a4 would also be the next second differences, and we can extend the table to the right as shown. Now we work upward, that is, we add 4 to the first difference 21 to produce the next first difference, which is 25. We then add this difference to the fifth term, 65, to predict that 90 is the next term in the sequence. This process can be repeated to predict additional terms of the sequence. For the example 5, what is next in sequence 2, 7, 24, 59, 118, 207? The third differences shown in blue are all the same constant, which is 6. Extending this row so that it includes an additional 6 enables us to predict that the next second differences will be 36. Adding 36 to the first differences, 89, gives us the next first differences, which is 125. Adding 125 to the sixth term, 207, yields 332. Using the method of extending the difference table, we predict that 332 is the next term in the sequence. Practice your understanding of math problems involving patterns with the help of these challenges.